Hello.
Hi. What happened to Tyler and?
Tyler's sitting down right now.
I'm here.
Dax
Okay.
is not here though, so.
Okay. No, it's too bright. Let me put this thing. Hey, Philip,
Hello.
we missed you a couple of days, I guess. You're not there.
Yes, I'm sorry about that. Last week I had the flu, and then this week is finals week at my school.
Okay.
So,
So we are missing Justin and
Here.
Nolan is just no, not Justin. Dax. Dax, yeah. Dax now Nolan and Dax. And Nolan I can see is just coming in here. Okay. So I need to do something. Share the screen. Now I lost something. Okay, so any questions, anything that you want to discuss about last time's? What did we do last time? I forgot. It was heap, right? Heap and heap sort. So we went through a few sort algorithms. We went through insertion sort, selection, bubble, shell, merge sort, quick sort, and heap sort. And all of them have their advantages and disadvantages. So if you have any questions, let me know. But now I'm going to switch to a different type of topic, which is called symbol tables. Can you see the shared screen?
Yes.
So symbol tables. Symbol tables are what essentially they're also known as dictionaries. So what we are trying to do in a symbol table is to throw things into an item. So if you look at this entire most of the stuff you do here, at least in this class, is all about like lots of collections of things. How do you put things and get things out? And of course, the next chapter will look at network, but we're still looking at collections. Meaning, like you have each collection has its own advantages and disadvantages. Sorting collections, searching through collections. So this is about searching through collections. Meaning, how do we throw things into a collection and then we can get things out a little faster than sorting. And so it's called a dictionary, and a dictionary or a symbol table is what's called a key value pair. So instead of now the data consists of two items, a key and a value. We are going to throw key value. For example, a student data could be key is the student ID and the value is the data that's associated with that student ID. So we throw things into a collection and we use the key as the thing to use to retrieve the data. We're using the key to retrieve the data. Right? So it's a key value pair. We are not so this is what a dictionary, like a dictionary, a word and a meaning. It's kind of So there are many places where you use dictionaries. Like, I mean, I can give you examples. For example, right? So a DNS lookup. A DNS lookup is a key value pair. Like, if you give me the URL, then I will give you the IP address. Right? So it's a key value. So we know what the URL is. We want to know the IP address, because when we do the communications, it's the IP address that matters, not the URL. URL, I don't care about what the URL is. The URL, well, you do know the URL, but that's the IP address is the one that identifies where the location is. But since people have a difficult time remembering IP addresses, we put it into a dictionary called domain naming service and look up there. I mean, you can see that. I mean, when you type in a URL, what happens is the computer sends a message to what's called the DNS. DNS service is something that is hosted by public companies, and then it sends back the IP address, and then it sends so it's the IP address that's needed, not the URL. So that's a key value pair. So we are trying to look up things like that. And where is the mouse? So other examples include like a dictionary, a book index, file sharing, accounts. Like you give your account number, then they'll retrieve the record. Right? Variables, types, routing tables, DNS, reverse lookup, all that stuff is what a key value pair is. Right? So we are trying to see if there is a way we can organize data into a dictionary, into a symbol table, that we can get things fast. And the disadvantages or advantages of different types of systems. Obviously, we already, so essentially in a symbol table, what we want to know is we want to be able to do these basic operations. So in a stack, we push and pop. In a queue, we enqueue and dequeue. In a symbol table, we put and get. We put things into a symbol table and we get things from a symbol table. So the terminology is okay, you put and get. Push, pop, enqueue, dequeue, put, get. Right? When you're putting into a symbol table, you're putting in two pieces of information, the key and the value that's associated with that. When you're getting from the symbol table, you're using the key to retrieve the value. So I'll give you the key. Can you retrieve the value? So you use the key as the parameter and then retrieve it. Deleting, you'll use the key and says delete this data from value from the symbol table. Contains, does this symbol table contain the key? Is it empty? Is it the number of items in the symbol table? And keys, meaning give me an iterator that I can go through and look at all the data in the symbol table. An iterator is and if I want to go through the entire dictionary, then I need an iterator. That's what an iterator does. It has two methods or three methods. Next, has next, is empty type of things. Then you'll go remove. Then you'll go through the iterator to traverse the elements inside the symbol table, and the iterator gives you a thing through which we can traverse a list of keys. So what can we use for this? From what we have known, what can we use? What type of data structure can we use?
A map.
A map is a symbol table. Sorry, yeah. If you like a map, that's another, like a dictionary, a map, a symbol table. They're all the same thing. So what type of so map is the abstract thing. What's the data structure? Can we use an array?
A 2D array?
A 2D array, right? I mean, a 1D array or yes, a 2D array. Any other? So if you keep or a linked list, right? Something like that. Now, if you keep a 2D array or an array, then we can look at the cost computations. Right? So we look at a 2D an array and see what the cost would be, and then we'll see, okay, can we improve on this, and see if there are other ways to keep track of these things. So
really quick, I just want to check something. Were you writing on the slides? Because if you were, I haven't seen any change.
And I have not been writing so far.
Okay, it just kind of sounded like you were, so I just wanted to double check.
Yeah, like, let me see if can you see this now?
Did you change slides? Because
No, I didn't, but I put an asterisk on the slide.
Yeah, I don't see
No, I didn't see anything change.
We don't see it either on the slide.
Yeah, I don't see it either.
Yeah, I'm still looking at the third slide.
That says conventions? No.
No, that's symbol tables.
No, symbol tables.
Okay, so that means it stopped transmitting the data. So let's stop sharing and come back and reshare this again.
Okay, yeah, I see the new slide now.
But hopefully, so this happened once before too, right? That it wouldn't.
Yeah.
Like I'll keep changing.
Yeah, I can't remember how we fixed it. It did happen before though.
Oh no, I removed their whatever their download add-on is, and then I reinstalled it.
Oh, okay.
So you see, when you start BlueJeans for the first time, it will ask you, like, do you want to run this program?
Oh yeah, okay.
So I redid that. I did that. So if this happens again, then I'll have to do that.
Okay.
So now let's see if we can go back. Can you see the slide here? Did it change?
Yes.
Okay.
Yes.
So in the next one, I wrote some scribbles, but so I was just describing so this is something you may have missed. So what a symbol table expects, if you're going to create an abstract data type for a symbol table, a map, it's essentially a map. Right? What you would expect to see, a put method that takes a key. Now can you see the writing scribbles?
Yes.
Right? Yes, a put method, a get method, a delete method, a contains method, an isEmpty method, size, and keys. And then additional things. And we'll see what additional things we can get, but this is what's minimum. A symbol table supports put and get. And that's what the main thing is. A push pop, enqueue, dequeue, put get. So certain conventions we are going to use here, that the values are not null. If the value is null, then that means that value does not exist in the symbol table. Right? So if you're searching with using a key in a table, and if you get a null, that means that value doesn't exist. You're looking for an IP address and you search in the symbol table, you get a null, that means that IP address does not exist in the map. Right? So values are null. So get returns a null if the key is not present, and put does not. So you're going to make sure that these are unique keys. Keys are unique. So you're not going to have multiple keys. If you're going to put the same key again with a new value, it's going to replace the old key. So it's replacing the old key, and that's what a put is going to do. So unique keys. So contains, we'll have to fairly easy to implement contains. If we get the key and if the key is not equal to null, then contains becomes true. Now we can use what's called, how do we delete from a symbol table? We have to remove that entry, right? If I say remove an entry, we have to remove it entirely from the entry. We have to take that out. In a symbol table, if you want to remove. Now we can do a lazy version of the delete. Is just don't remove the entire entry, just make the value to be null. Right? So that's so I don't want to remove it. I say, oh, let's look. I know it needs to be removed, but I'm just to mark the value null. That means that entry does not exist. Right? So we can do that's a lazy implementation. That I'll come back and do it, but right now I'm going to mark it null. Right? So there are a few things with symbol tables. So we know the difference. There are three important methods that we need to know about here. First is the compare to method. We already know what a compare to method does. What does a compare to method do?
It lets you compare an object against an object of the same type.
Of the same type, and returns three numbers: less than 0, right, greater than 0, and equal to 0. Right? So if it is less than 0, the first number is less than that first number, greater than, and equal to. Right? So it's less than 0. Now the equals method compares to see whether two objects are similar, identical. Right? So equals method would compare to apple. Now they don't compare it equality, not the equal to sign, but the equals method compares for similarity. And then hash code is we'll look at what a hash code is at the end of this chapter. We need that too. So best practices, make sure that the keys don't change. Keys are immutable. You want to use objects which are immutable. Because if you have a key and if you can change the value of the key, then that changes the whole thing. So the usual practice is to say keys are immutable, like strings, integers, doubles, they're all immutable. And use keys that are immutable. So once a key is a constant, essentially. A key is supposed to be a constant. So if you're going to use a key, use something that remains a constant. Equality test. Right? So if you're going to do the equality test, these are some conditions that you know that there's something called overwriting the dot equals method. There's an equals method in the object class. Right? You're aware of the fact that there's the toString method. It returns a string. There's an equals method. So what's the equals method supposed to do? By default, what does it do? And if you override, why do you override it? And what are you supposed to do? Go ahead, Justin.
By default, it compares data values, right? So like not data values, sorry, but the memory location of objects.
The reference numbers.
Yeah.
And then
you want to override it to compare the actual contents of the.
You want to override it? Yes, you want to override it so that, like, if there are two strings, if you should know. I mean, if there are two strings that have the same identical contents, right? Oops, why? Why is it doing that? There are two strings that's identical constant, like identical values. So we know that if you compare them with the equals method, the equals operator, is S1 equal to S2?
No.
Most likely, I mean, S1 is not, because they are not the same object.
If
right?
you do S2 equals S1 though, right?
So if you want to compare whether they're identical, yes, you need to say you can either do S1 dot equals S2, that with the equals, right?
No. But if in the declaration of X or S2, if you instantiate it to be S1 and then compare,
then it would be the same.
You're right. Okay.
Yeah, because you're not really creating a separate object. You're just copying the reference number from the first box into the second box.
So dot equals would return true in that case, right?
No, the dot equals will return true in both cases.
Oh, okay.
Right? So what you did was, when you created the first one, you created a variable called S1. Whenever we create an object, and then there's an object that contains the string you want to. That's an object. So you have a reference number for this. Let's say that reference number is 2136. The object reference number. That's the one that gets copied into this cell. Right? So that's what the first line. The first line does that. If I say S1 equals that, that's what happens. If you create the second line, you're going to create another line. Okay, so let me actually, I'm scribbling all over here. Let me go to a new slide here. So let's see the difference here. You can see the scribbles, right? I am scribbling something.
Yes.
Right? So if I say S1 equals hello, it does is it creates a variable name called S1, and then an object in the heap where it contains the string hello. That's an object, and the object contain all objects are referred to using their key value, which is what the key is, the reference number. We put the reference number into this cell 2136. Now, if I say that's what happens with the first line, so this reference number refers to that object. If I say S2 equals hello, again, I don't know why it does that. So then throws this random stuff. Right? And if it does the same thing, because I'm actually, if this would, so it'll create the same S2. I'm being a little sloppy here, but this is what approximately happens. Sometimes the way you declare strings, it may not do that. But so you create a second string. For all objects, it'll do that. For any object, if you use the word new, that's what it does. Creates a new object. This is a different object. It has an object and it has a reference number, let's say 6491. And it puts it down here. Now let's say we create a third variable, S3 string, and say S3 equals S1. Now if you do that, what happens? Create a third box called S3. What did we put inside S3?
Two, 136. Yeah.
2136, right? So we are copying the contents of the S1 into S3. Right? Now, if I say, what about this one? S1 equal to S2, true or false? Are the contents identical?
No.
False.
No. They're two different numbers, right? Because S1 contains 2136, S2 contains 6491, so they are not. If I say S1 equals S3, are they the same?
Yeah.
the same, right? So that's why you get an equals, because you didn't create a second object, you just copied the reference number. Now you're just comparing the reference numbers to see are they identical. That's what the equality of equals operator does. Because in this line is just an assignment operator. Copy the contents of S1 into S3. Right? So now, what about S1 dot equals S2? True or false?
False. Right? Because a non-overridden dot equals just compares reference numbers.
Yes, but because it's a string class.
Oh, it's overridden. Okay.
It automatically overrides. Otherwise, yes. If you don't override it, that would be true.
Okay. Yeah. So it's true then.
Because string class already overrides the class method, so therefore this becomes true. What about S2 dot equals S1?
That's also
I think it'd be true as well. Same thing.
Yeah.
It's got to be true, right? It's the same thing. You should, right? So that's what these properties are trying to tell us. Like when I say these are the properties that we need to have, right? So this is what we are trying to say. Reflexive, and right. So
the screen is frozen again.
It is.
My screen is frozen again.
Are you writing something right now? Because the last thing we see is S1 dot equals S2.
Yeah.
Okay, so I switched screens.
Yeah, that's what I thought.
Okay, I'll do this again. So I need to.
Thank you.
Thank you for letting me know, because otherwise I wouldn't know. I just keep. Is it? Can you see the new screen?
It's on a quality test right now.
Yeah, I think I kind of know what has happened, because I told you that I reinstalled my backup. I wiped out the hard drive and reinstalled my version of the thing. So it still has that older version of BlueJeans.
Okay. That makes sense.
So now, can you see the screen now?
Currently it's on a quality test. Is that right?
What about the others? I thought Philip said he can.
Yeah, I can see it.
It's on a quality test right now for me.
Equality test.
Yeah, it's all on a quality test. I was just double checking.
Oh yeah. So now I just switched that case. Yeah. So now if I switch, can you see the stuff?
I still see a quality test.
Yeah, so do I.
Yeah, no switch for me.
It's still an equality test. Okay.
I still have a quality test.
That's fine. So I got to fix that today. So essentially you can see that what we are trying to do here is that it is reflexive, and reflexive meaning it always has to say x dot equals x is true, right? Equals symmetric. If x dot y equals true, then y dot x should equal true. And this is one of the important things. X dot y equals true and y dot z equals true. X dot z equals true. Now, if you want to know how to write this equals method for a class, this is how you would do that. Let's say, for example, you want to create two classes called a class called date Right now, if I'm going to use date as a key, I want to make sure that it's final so that no one changes it. So I mark it final. What does a final keyword in front of a class mean?
Does it mean it can't be extended?
Non-editable.
You cannot extend it. You cannot create subclasses of it, right? So a final keyword means you cannot create further subclasses of it. If you try to create a subclass of string, for example, that wouldn't let you do that. So it implements a comparable interface. And the way to override the equals method is like this. First, this is a standard practice. If the object is pointing to itself, return true. That's for, right? If it is pointing to itself, return true. If the object is null, always return false. And then you check the key attributes from the two objects. The important attribute that you think need to be identical. Before you do that, make sure that both objects belong to the same class. Right? Both objects belong to the same class. That this object dot get class is the same as the other object dot get class. If both are, so why do we not use the instance of method but use the get class method, the instance of keyword? There's a keyword called instance of. Go ahead.
I guess if one of the objects is like a subclass of the other one, then instance of might return true in that case.
It will return true. It'll return true. So if you're comparing a dog and an animal, like animal dot equals dog will return true, whereas dog dot equals animal will not, because so that's going to be non-reflexive.
But dog dot instance of animal would be true.
Right. Because instance of would be true, yes. But the get class returns the exact class of it. So make sure that they both belong to the same class, and then compare the key attributes. And if all the key attributes are true, return true. That's how you would override the equals. So the equals is an important attribute of the key. Because we are going to compare based on the equals method. Right? If two keys are considered the same, if the equals method returns 0. So the easiest, of course, the one we can see is, I think it must be frozen now, is it?
Yeah.
Yes.
Well, I have to do this. But today I'll have to go through this every time. How is it now changed?
Yes, it's on equals design, and your cursor is moving. So.
Yeah, for a few minutes, few seconds, it will move. So the equals design, that's the standard practice we do. Optimize, check against null, check to see the objects of the same type, cast, and compare all the significant fields. If they're primitive fields, use the equals operator. If the field is an object, use the equals recursively. And with primitive keys, the key is a significant field, key is an array, apply to each entry. And do not use, or for most part, you should not use fields that are computed that depend on other fields. And when you're doing an equals test, compare the most likely field, the one that's likely to differ, compare it first. Right? Like if you're comparing date, year, and month, whichever that's likely to differ, compare it first, so that you don't have to waste your time comparing the rest. And consistent. X equals y only if and only x dot compared to y equals 0. So it switched? No.
Yeah, it switched.
So let's look at a symbol table and see how it works. Let's say, for example, these are the keys I'm trying to insert into the symbol table. And let's see how this thing gets inserted. So initially, the symbol table has, we're going to create an array. We're going to create an array. So an array, like a two-dimensional array, there's a key. You can imagine that it's kind of like a two-dimensional array. There's the first column is the key, and the second column is the value. Insert S. You insert S into the key thing. Now this is of course being maintained, right? It's sorted. So you insert S into the thing. S has a value 0, so you insert that. Insert E. E has a value 1. Initially, E has a value 1. So let's insert 1 into this. So E has 1. A has 2. So A has 2. Right? So the one we saw. So it's going to be S. So if I'm going to write it like this, S had a value 0. E had a value 1. I'm still scribbling on this thing. A had a value of 2. R has a value of 3. C has a value of 4. H has a value of 5. And then you insert E again. When you're inserting E again, E is already in the symbol table. So you don't reinsert it. You cross off the old value and put the new value. Because in the symbol tables, so before you insert, check to see if the key is already there. If the key is already there, don't insert it. Cross the old value, put the new one in. Replace the new one. Right? So E gets to be 6. Now X gets to be 7. A gets to be 8. No, A is A already? Yes. A is already there. So cross off the old A and then put the new A here. Right? So M, put the M here. M is 9. P is 10. Like that. So symbol table, this is how the symbol table is supposed to behave. Whenever we put into the symbol table, it searches through the entire table, and if it finds the key, replaces the old value with the new value. If it doesn't find the key, it adds it into the symbol table. Okay? That's what symbol tables are supposed to do. And as we saw, we could, I'm going to skip these slides, we could create a sequential list like this. Right? We could create an array. And we could create an array like this. Right? It could be a sorted list or an unsorted list. We have seen that stuff. So there's nothing here to, we know how to insert into a sorted array. We know how to insert into an unsorted array. There's nothing tricky about it. Okay? So the only thing we have to look at is what the cost would be. If it is an unsorted list, if you're going to maintain a symbol table using an unsorted list, did the slide change?
No.
How is it now?
You can see it.
Okay. So if you're going to use an unsorted list for a symbol table, what's the insertion search cost?
Same for a normal insertion sort.
Yeah, right. It's you have to. Why do we have to? Why? So you have to. The worst case would be n. You'll have to go through the entire list. The average case would be half n. What about the insert cost?
It's going to be n worst case and average case.
In both cases, it's going to be n.
Isn't that what it says to the table?
Why?
Oh. Well, if it's unordered. If it's unordered, you shouldn't have to search when you insert, though.
Well, you have to search
the key exists. Oh, search
Yeah.
to see if the key exists, right, yeah, okay. Never mind.
So it's always going to be n. You have to go through the list
Yeah.
to search the key before you insert. It's always going to be n. Right? So whether it's the worst case and the best case, I don't know. It doesn't exist, so I'll have to search. The average case also, the average insert, like average case, right? That an insert operation happens, it's going to be that. So we can use, if you want, we can use a sorted list, right? If we use a sorted list, then we can do binary search and make the search easier. Right? So you know how a binary search works, right? So if the list is sorted, you can use a binary search, and that should. So there is nothing that's tricky about creating a binary search. So that's what a binary search would be, and that is the cost would be something like this. So the insert, I switch slides.
Yeah, we're good.
Yeah, I saw it.
So the insert is going to be, if it is an ordered array, the insert is going to be, the worst case is search is log n.
Yeah, and then insert's on.
Insert is n, because why is the insert n?
You're still searching the entire array.
No, but no, once you have searched, you're going to insert.
Oh. You still have to check, you still have to check the key.
So you have to do a log n to see whether the key exists, right? That's the same for both cases.
Yeah.
You have to do like an insertion sort, basically, like where you have to go through everything and swap it through.
No, so you insert and move everything down or up or down by one.
Right.
So
Right.
if you're going
So
to
I guess
maintain, right?
Right. So insert maybe is sort of like log n plus n, but
That's
you just write it as n because it's the greater part.
That's right. I ignored the log n part of it. The insert is n because I want to maintain this as a sorted array. That the worst case would be I insert the element at the beginning of the array, and then all the elements have to be moved back by one. On an average case, the insert is n over 2 because the cost of insert is because I need to shift everything once something's been inserted. The search is good. Search is log n, but the insert is not good. Right? Because the fact that I have to move things a little bit. The last thing that we also would like to have in a symbol table is some of those ordered operations. Right? In addition to get, put, contains, empty, size, all that stuff, we also would like to see some of these types of operations. These are called ordered, some ranking operations. Like for example, I want to be able to retrieve the minimum key, the maximum key, the floor of the key, the ceiling of the key, the rank. Rank meaning the number of keys that's less than this key. Right? So I want to create a data structure that would not only give me the get and the put and the delete and the contains, but also additional ordered operations like the key, right? The flow, the ceiling, the rank, select, identify, select the key of rank K, delete the minimum, delete the maximum, all this stuff. Can we do all these in the symbol tables we have seen so far? If you're going to maintain a list or an array, can we do these things?
Yeah, I mean, why not?
Can we do a minimum? Yeah, that takes n. Can we do a maximum? I mean, if it is unordered, yes. Yeah, ordered, unordered, you can. But what about things like rank? Meaning, how many keys are less than the key I just looked at? In an ordered, yes, I can count. In an unordered, yes, I can count again, but the entire list. Right? I have to go through the entire list. Right? So I can do all these things. I can do delete max, delete many. So yes, it can be done. Let's see if we can do it better. Right? So we can create a list. We can create an array. We can do all these things, and the cost is more likely to be in the order of n, because every time we may have to traverse the entire array. So is there some type of a data structure that we can use that's better than using an ordered list like this? So these are some of the costs that you would see if you create a set of ordered operations. If you notice that this thing changed. Right? So I didn't spend too much time on this because this is something that's kind of common. Like you have worked with these things many times that we don't want, but we want to know what a symbol table is and what's expected out of a symbol table. It's a dictionary or a map. A map is also a dictionary. It's a key value pair. So you insert using a key and a value. So you insert a key value, you select based on keys, you retrieve based on keys. And the important thing about the keys is that they must support the equals method. That because if you create two keys are considered identical if the equals method returns 0. Right? So equals, we need to be able to override the equals method correctly. Because if the equals method is not, if you don't override it correctly, the symbol tables won't work. You can insert, but you won't be able to get it because the keys won't match. If you recreate the same key again, the keys won't match. Right? So that's what a symbol table is, and we can certainly use arrays and linked lists. So let's see if we can do this better, and I'm going to introduce what a binary search tree is. A tree structure. Right? So we are going to create something called a tree. We know what a heap is. How does a heap look like? Isn't heap an array? I mean, a heap, yes, we can use an array, but a heap is like a tree with the property that the roof node, right, the root node is always higher than the children, right? Isn't that how we created the heap? A heap was, I'm scribbling something on the screen if you can see it.
Yep, we're good.
Right? So it's something like that. So you can, so if you have 50, if this key is 100, the child nodes, this could be 90 and this could be 30. Right? And the child node of the left child could be 80 and 70, and the other one could be 20 and 10. This is what a heap is. You can visualize a heap like that. A heap has a property that the root or the parent is always higher than the child nodes. A binary search tree is like this, except it has a property that the left children are smaller than the parent and the right children are larger than the parent. So this is a heap. Right? So this is what a heap. So a binary search tree is going to look like this. So we have, let's say if this was 50, this could be 30 and that could be 70. And this could be 20 and that could be 10 and that could be 60 and that could be 80. This is what the binary search tree is. See the difference between a heap and a binary search tree.
Wouldn't that 10 have to be something like 40?
Yes, I flipped it. Thank you. Well, I'm not the only one. Well, thank you. Where's my eraser? Right. So yes. So the left children are always smaller than the right. 40, I wrote 10, but fine. Right. Now does it satisfy the property of a binary search tree? Did I miss something up? Nolan?
No, that's fine.
It looks okay. Okay. Right.
Yeah.
So the property is that the left children are smaller than the parent, and the right children at every point are greater than the parent. Right? So if we can maintain a structure like this, and if we can somehow find a way to maintain this, then when you're going to insert something, let's say I have a symbol table that looks like this, and I want to insert the key 55. Right? So I'll look at the key and says this is 50. So if the key exists, where would it be? Would it be on the left tree or the right tree? So I want to insert the key 55 into this.
So you'd look on the right, I guess.
You look on the right and you don't use, so because 55 is greater than 50, I look on the right and no, it's not. So what I find is 70. Well, it's not that I was looking for. Then, so now I look on the left of 70. I'll find 60. Now, because 60 is still larger, if the key had been there, I'll still look on the left. I don't see anything on the left. So I insert the new key down here. Right? So let's insert some other key. Let's insert give me a random key.
78.
78. So insert 78. It has to be on the right side. Go to the right. Well, that's a 70. A 78 is larger than 70, so you go to the left. It's 80. It's smaller, so we insert it down.
Right.
You go to the right and the left of 80. Yes.
Wait,
right. You go to the right. So you go to the left, yes, go to the right of 70 and left of 80. Right? Now let's say you want to insert 60 again. Right, insert 60. So you go, you keep looking and you find 60. So you stop there and update the value because the key is already there. So I don't have to insert what's already there. So I'll keep looking to see if you find the key, just update the value. If you don't find it, so that means if you reach the leaf nodes, if you reach the leaf node without finding the key, then that means the key does not exist in the symbol table. So therefore you insert it at the very end of the leaf node. Right? So if you're going to insert 15, you'll go 30, you'll go 10, and you'll insert it as a right child of 10, that's 15. If you're going to insert 12, that's going to be 30, 10, 15, that's going to be the left child of 15. Right? If you want to insert 79, that's going to go like that. 50, 70, 80, 78, right child of 78. Like that. Right? So this is what a binary search tree is. A tree, it's got two children, a group of left children and a right children. All the left children are smaller than the parent, and all the right children are greater than the parent. Now, as you can see, I'm trying to flatten the height of my search. I mean, if you can imagine that what the binary tree, what I'm trying to do is, I'm going to take it and flatten it to a log n height. Right? So from n, all my path from the root, if this is a very well balanced tree, if this is a balanced tree, the path from the root to the leaf is log n. Right? So I'm trying to go from the cost n to a cost of log n. That's what I'm trying to do. The next 2-3 weeks, we are going to discuss different forms of binary search trees. Right? A normal binary search tree, how do we insert, how do we retrieve, and then what's called a balanced tree. A balanced tree is pretty tricky. So we'll start on the balanced tree, but we may not be able to finish that. Okay, so I'll let you go. And if you have any questions, you can ask me quickly.
Great, thank you.
Thank you.
Thank you.
Thank you. You're welcome.
Oh, I just wanted to inform you for this last assignment, I have the handwritten part done. I was just working through it, and I ran into a small problem where for some reason I don't have correct recursion. So it'll just keep running through the same function. So actually, no, there's the problem. So now I'm going to need like 5 minutes to rewrite this and answer the questions. Then I'll have it for you.
Okay.
Just wanted to let you know.
Can you access the old eCollege pages from fall?
I tried the other day and it wouldn't let me, but I can try that right now and see how that works. Just have to wait for it to load. Okay, here's the one from fall. I'm gonna try and get into it. No, it says it's not an active course.
Okay. So then I'll look at the ones which you haven't submitted. Then I'll email. Whatever you have, give it to me. Then I can give you the ones you don't have.
Okay then.
So like, and there are two ways. I can either check the grades and see which ones you didn't submit. I can send them to you. But if you have some with you already, then I can ignore those. Not send them to you.
Well, I have some, but I just wanted to look at the assignment list to make sure I'm fitting all the requirements.
Okay.
So would you mind just checking all the ones I'm missing and send me those so
okay,
I can make sure?
I'll do that then.
All right then. Thank you.
You're welcome.